Okay, hello everyone, and welcome to Lecture 9 of Chemistry 3120. Today we're going to wrap up Chapter 23, and it's sort of a wrap-up chapter, and I'm going to talk just very briefly about some reactions that we can use to control chemoselectivity. So this chapter has been focused on chemoselectivity. I hope you've found it pretty interesting. So just to highlight what we've been talking about, we started this unit by introducing chemoselectivity. And then we looked at protecting groups. You learned a lot of new protecting groups, why they're used, how they're useful. Then we looked and spent quite a bit of time on reductions. And specifically, we looked at metal hydride reductions, catalytic hydrogenation, and then we looked at dissolving metal reductions. And then we just finished oxidations. And you looked at a number of different ways to oxidize. And the last thing I just want to talk to you about are just some what I call final thoughts on controlling chemoselectivity. Or let's just call this on controlling selectivity. So maybe the first reaction we'll look at are two things I just want to bring to mind. Is this reaction here, or this molecule here. And let's say we have a strong base present. Which acidic proton are we going to remove first? So on this molecule here, you have this proton that's acidic. This has a pK of around 15 to 16. And here we have an sp terminal alkyne, which has a pK of around 25. So this is much weaker compared to this one. So this is the stronger acid that's going to get removed first. If you wanted to then remove this proton here, you would need to add a second equivalent of strong base. Then you could generate this dianion. The last thing about this reaction here is that if we then made that dianion and then we reacted it with an electrophile, which anion is going to react with the electrophile? Is it going to be the O- or is it going to be this alkyne carbon anion? Think about that for a second. Or maybe it's random, maybe it's 50-50. Usually that's not the case in organic chemistry. So the anion that's formed last, which is this one here, the reason it's formed last is because it had a higher pKa, meaning that the conjugate base here is less stable compared to this one. So therefore this is the one that's going to react first with that electrophile. Okay, so something worth remembering is that the anion in these types of reactions where you do multiple deprotonation, the anion that's formed last will always react first when you add electrophilic substrates. Here's a final reaction for this unit. And let's say we're going to react this with this benzoyl chloride. And let's say we do this under basic conditions. So let's say we have triethylamine in here, and then on the right side, let's say we're doing this under acidic conditions. So let's just say pH, less than 5. What is the product going to be? Let's go this way first. So we've learned, if we think back to lecture 2, one of the first examples I gave you was a reaction with a nitrogen nucleophile and oxygen nucleophile. And you learned that nitrogen is a better nucleophile. It's less electronegative compared to oxygen. So therefore, you can imagine that these nitrogen electrons are going to be willing to come in, react here, tetrahedral intermediate comes back down, kick off the chloride, and you'll get that benzoylation over here, as opposed to that primary hydroxyl group. And that's exactly what you get, right? So nothing funny here. Okay, that's the projected product, and indeed that's what you get. Now, if you do this reaction under acidic conditions, and something different is going to happen, right? I wouldn't just be putting this up and then the same reaction happens. That would be very silly. So what's going to happen here? Under acidic conditions, we start to go below 7. We start to generate a lot of protons around, okay? So I'll just draw protons attached to some type of structure here to give an acid. Now, I've taught you that the nitrogen is the better nucleophile, right? But if you do this reaction under acidic conditions, you actually generate the ester, where you get the alcohol reacting here. And then you might be saying, well, wait a minute, why is that the case? Because Professor Desaulniers told me that the nitrogen's the better nucleophile. Nitrogen is the better nucleophile, but why is this the product? The reason this is the product is because nitrogen is the better nucleophile, but you just now have a lot of protons present in solution. So what happens is that the nitrogen, because it's a better nucleophile, gets tied up and picks up a proton. And when it picks up a proton, you have a nitrogen that has 4 bonds, it's positively charged. This is now not a nucleophile. Therefore, because it's not a nucleophile, it can't react, and the only nucleophile that can react is the alcohol. So I want to also just emphasize the fact that you can control a lot of chemoselectivity reactions by changing things like pH. Okay, the electronics never change. Nitrogen is the better nucleophile in each of these cases. All we've done is we've said, here, pick up this proton. That's your electrophile, that's your bait, and then alcohol can come and react to make the ester. Nitrogen's a better nucleophile. I won't write but, I'll say so. At low pH, it picks up a proton. All right, so that's all I want to talk to you about with respect to chapter 23, chemoselectivity. So hope you enjoyed that chapter, and see you soon.